Today's AI coding assistants are remarkably fluent. They can generate complex functional code in seconds. But beneath that fluency lies a critical flaw. They frequently output exploitable weaknesses, giving developers misplaced confidence in the security of their applications. To fix this, engineers generally rely on one of two approaches. The first is training time mitigation, like SecVec-Coder, which attempts to optimize model parameters directly during the learning phase. These methods work, but they demand massive computational resources, specialized training data, and long, expensive optimization runs. The second approach is inference time mitigation. Here, the base model stays frozen, but generation is guided through constrained decoding or external security modules. The cost of this guidance is paid on every single token. Evaluating constraints introduces significant latency overhead, severely slowing down the code generation process for the end user. This leaves the industry trapped in a frustrating bottleneck. You can either pay exorbitant compute costs to train a secure model, or ruin the user experience with slow, constrained decoding. Achieving truly trustworthy code that is simultaneously functional and secure, requires a structural solution. We need a way to edit model weights directly, without full retraining cycles or inference time modules. This is the premise of SecVec-Coder, a framework that hard-codes security directly into a coding language model using task vector arithmetic. Rather than relying on continuous training or auxiliary modules, this approach modifies the weights themselves. Deployment proceeds with standard autoregressive decoding, meaning it operates with zero architectural overhead. The performance data shows a sharp increase in trustworthy code completions across 3 major open-source model families, achieving up to a 36 percentage point improvement over the base models. Crucially, this happens without the standard penalties. Because standard decoding is preserved, latency remains within 0.6% of the original model, and the vector calculations require up to 12 times less training compute than competitors. By treating alignment as a targeted matrix operation, SecVec-Coder bypasses the security latency paradox entirely. A task vector defines a direction in weight space for a specific behavior, calculated by subtracting the base model from a fine-tuned model to isolate the delta. For trustworthy code, we extract 2 vectors, one fine-tuned on secure code and one on vulnerable code. Isolating the insecure vector gives us a mathematical contrast. We need this negative reference point to accurately identify and suppress undesirable implementation patterns. The viability of this entire method depends on the precision of these vectors. If the secure and vulnerable directions are highly correlated, the arithmetic fails and steering the model becomes impossible. It might seem logical to build these vectors using standard supervised fine-tuning, or SFT, but output analysis reveals a limitation. SFT-derived secure and insecure task vectors exhibit extremely high cosine similarity and global sign agreement. Geometrically, these vectors point in nearly the exact same direction, failing to distinguish between writing functional code and secure code. This happens because the SFT loss function treats all tokens equally. It spends most of its optimization budget learning general syntax and shared structure, rather than focusing on the specific lines of code that make a function secure or vulnerable. Because the vectors are highly correlated, they are mathematically entangled. Subtracting the vulnerable vector inadvertently subtracts the model's ability to generate functional code at all. Standard fine-tuning is too blunt to decouple these behaviors. We need a method that ignores the shared syntax and focuses entirely on the security-relevant differences. This decoupling is achieved through localized preference optimization, or LPO. This diagram illustrates the LPO training pipeline. The process begins with paired completions, a single prompt answered by both a secure and a vulnerable implementation. LPO applies a localized mask to identify exactly which tokens differ between them, leaving the shared, functional syntax lightly weighted. By focusing the supervision signal exclusively on the disparate tokens, it prioritizes security-relevant choices without altering baseline programming logic. The geometric result is stark. The secure and insecure task vectors separate entirely, dropping their sign agreement and becoming negatively correlated. Because the behaviors are now pointing in different directions in weight space, we can surgically subtract the vulnerable properties without degrading the model's core ability to write code. With the vectors isolated, we must recombine them with the base model to steer towards security while perfectly preserving problem-solving capabilities. This visualization shows three steering operators. First is negation, on the left, subtracting a scaled insecure vector from the base model. But moving away from the insecure direction often pushes weights out of the functional zone, reducing the ability to generate working code. The optimal approach is secure anchored steering, shown on the right. Rather than modifying the base model directly, this operation starts at the secure fine-tuned model and subtracts the insecure direction from that anchor. The amount of suppression is controlled by a scaling coefficient, theta. Tuning theta determines exactly how far the final weights are steered away from vulnerability. Secure anchored steering succeeds because it grounds the operation in a proven, functional state before applying the negative gradient, carefully balancing capability with safety. To validate this balance, the output must be measured using SecPass@1, a metric that strictly requires a single generation to pass all functional tests and be free of static analysis vulnerabilities. This chart displays SecPass@1 performance across the models. Applying secure anchored steering with a theta of 1.5 consistently yields the highest rate of trustworthy code. These gains remain consistent regardless of sampling temperature, confirming the arithmetic robustly shifted the model's distribution. We can also see that the steered models successfully generalize. In these test scenarios, the models correctly suppressed software weakness types they were never explicitly trained on, improving unseen vulnerability avoidance by up to 39 percentage points. This indicates the algorithm is doing more than memorizing specific patches. The task vector edit has remapped the model's internal representations to favor secure implementations, even when the specific weakness type is unfamiliar. All of these gains are achieved without the traditional penalties of alignment. Because the final steered model uses standard decoding, its inference latency clusters tightly at the 0% baseline. There are no external modules calculating constraints on the fly. It is also highly efficient to produce. Creating these vectors requires a fraction of the data and significantly less compute time than training an equivalent safety adapter from scratch. This establishes a practical methodology for continuous model alignment. We can apply lightweight, modular behavioral updates directly into model weights without enduring massive retraining costs. The secure anchored operation provides a specific, replicable template for resolving interference between core model functionality and targeted security preferences. By addressing software security not as a decoding constraint, but as a geometric property of the weight space, developers can finally deploy coding models that are as fast as they are trustworthy.